In this video, we're going to talk about Redington immunization. All right, so we've already encountered two different types of risks when we look at trying to match liabilities and assets. We've seen reinvestment risk if the yield rate falls. We see price rate if the yield rate increases. So what we really want to try to do is counter those types of risks, and we're going to use what's referred to as Redington immunization to do so. So, essentially what we're going to do is, if we look at the surplus of the firm, what we're going to end up doing is create a local minimum at a particular yield rate. Okay? When we can calculate that local minimum, then we know that no matter what, if the interest rate changes, the surplus should go up rather than down for a small change, right? Because the local minimum would be the absolute minimum that we would have of the surplus. So if the interest rate changes in either direction, we want the surplus to go up, meaning that our assets should be higher than our liabilities in each case. To make sure that happens, we're going to assume that we have the surplus as 0 to start with, so that we have an even present value of our assets and present value of our liabilities, matching assets and liabilities exactly. Now we're going to make sure that we have a local minimum. So if we're going to have a local minimum, we need to make sure we have a critical number. Critical number occurs when the first derivative is equal to 0. So now looking at the previous equation, if I differentiate this with respect to I would have the derivative of the present value is equal to the derivative of the, present value of the assets equals the present value, the derivative of the present value of the liabilities with respect to the interest rate. I could certainly multiply both sides by -1. That doesn't change. And since the present value of the assets and the present value of the liabilities are the same, I can divide both sides by that quantity. And the reason I do that now is I recognize these fractions. The first one is the modified duration of the assets. The second one is the modified duration of the liabilities. So, to make sure that we have a critical number, we want to make sure that those durations are actually equal. Now, we want to make sure we have a local minimum. By a second derivative test, we get a local minimum at a critical number if when we take that critical number and plug it into the second derivative, we get a positive number. So now going back to the original equation here, if we take the second derivative, we'll get the second derivative of the present value of the assets is equal to the second derivative of the present value of the liabilities. Again, if we divide both sides by the equal quantities, we get that this ratio is greater than this ratio. And now we have modified convexity of the assets is greater than the modified convexity of the liabilities. Now notice I didn't use the notation for modified duration or modified convexity. In these, pardon me, these values here can be computed using modified duration and modified convexity like we have them written, but you can also use Macaulay convexity or duration and you'll get the same answers, and usually we'll use the Macaulay versus the modified anyway. Alright, so let's do an example. This company has a liability that it pays $2,000 in 2 years. We want to guard against small changes of yield rates around 10%. So again, that means that at 10% interest, when we're calculating these things, we want to make sure if we have a small drop or a small increase, we're still able to cover the liabilities with the assets that we have. All right, we're going to choose some 1-year bonds and some 3-year bonds going on either side of 2 years. We're going to calculate how much of each bond should be purchased to achieve immunization at a 10% annual effective interest rate. All right, so we want to make sure that we have the present value of your assets equals the present value of your liabilities. Say we choose purchase X of the 1-year bonds and Y of the 3-year bonds. Then present value of X plus present value of Y has to be present value of 2,000. And now for durations, these are zero coupon bonds. So the duration of a zero coupon bond is just the term of the bond. So the duration of the first one is just 1. The duration of the second one is 3. Duration of the $2,000 liability is 2. Subtract the two equations to get 2y over 1 plus 1 cubed equals 2,000 over 1 plus 1 squared. Solve for y, you get 1,100. Plug that into either of the equations. I chose to plug it into the first. You get 90909 for x. Now notice we didn't use the convexity piece. The reason why we didn't use the convexity piece is that you can actually show that if you've got a single cash liability being met by single cash flows, one below and one above, you're always going to achieve immunization. But we can actually see that the convexity condition is also met. If we take the convexity of the assets and the convexities of the liabilities, we can see that they are in what we need them to be. So again, the convexities are just going to be the squares of the time for Macaulay because it's just a single cash flow. So we do 1 times the x over 1.1 and 9 times the y over 1.1 gives us the 8264.46. We do the 4 times the 2,000 over 1 plus 1 squared. That gives us a 661157. So the convexity condition is also met. So for the values x and y, we get that local minimum on the yield curve.